All right, this is our last little tip or trick, and it's using less than, greater than, and squeeze theorem to see if a sequence is convergent or divergent. So we've done this before with other things, but now we're just applying it for sequences. So if you look at our little a sub n equals cosine squared of n over 2n, if we say that this is convergent, right, and we know it's convergent, then what we can do is find something that's a little bit bigger than it, or bigger than or equal to it, and say that that's convergent. And if that converges, then so does our sequence. So we know that this is less than or equal to 1 over 2 to the n. And that's because cosine squared of n as well is also less than or equal to 1 over 2 to the n. And you do want to keep it kind of tight, like this. So if you look at it here, this is our 1 over 2 to the n. That's in blue. And you can see our sequence is between there. It's above 0, so I don't have to worry about that, right? It's bounded by the bottom of 0 because it's cosine squared and 2x. So I don't have to worry about squeeze theorem. I can just pick a top value. So I've got that here, and you can see it's just kind of like it is kind of like squeeze theorem where it's getting pushed right on in there, but it is approaching it. So if we can show that this one converges, then we know that the red one also converges, and they're really close in their limit. So we can now do the limit as n approaches infinity of 1 over 2 to the n. And if you remember this, we want to rewrite it till we have a base because we have a power of n. So this would be 1 over 2 to the n. And we know that rule, that as long as our r is less than 1, this goes to 0. So we can also now say that the limit as n approaches infinity of a sub n is 0, because this is going to always be positive, so it's just applying that kind of. So our function is convergent. Our general term, that is. So now what if we want to find something's divergent? Well, what we do is we find something that is smaller, so we want to use greater than, that this is greater than, and we find something that's smaller than it. So we want to know that our general term is greater than or equal to something. And if we can show that that smaller thing is divergent, then we show that our general term is also divergent. So the best thing to do is to plug these in your calculator. Either use Desmos or use your graphing calculator under sequence mode, and you can actually see whether it's going to be off to divergent or whether it's converging around some line. And then after that, you can also use the calculator to find some other term that would be less than it and show that that one diverges, which means this one would diverge. So in order to do that, we need to find out what is making this general term up. So this would be 1 factorial over 2 to the 1, and then 2 factorial over 2 to the 2, 3 factorial over 3 to the 3, and so on. So this is really just 1 over 2, and then that would be 2 times 1 over 2 times 2. And so this would be 3 factorial over, this is 2 actually, and 2. 2 times 2 times 2, and then 4 factorial over 2 times 2 times 2 times 2. And so you can kind of see what's going on here. And this would continue on until we get all the way to the end of n. And so that would be n factorial, right? Which would be 1 times 2 times 3 times 4 times 5, dot, 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 n factorial over 2 to the n. And now if we write out all these 2's, that same way, it would be 2 times 2 times 2 times 2 times 2 times 2. See, you really want to write these out to see what's going on here, and it'll start to show you a pattern. So you can see that each of these, 2 over 2, 1 over 2, 3 over 2, 1 over 2, 1 over 2, they're matched. So our n factorial is really just 1 over 2 times 2 over 2 times 3 over 2 times 4 over 2 times 5 over 2 times, that's a 2 at the end, all the way to the n. Why do I have an n factorial there? It's already done. N over 2. And so now we can use this to make something smaller. So what I want to do is I can't get rid of any fractions because the fractions make things smaller. But whole numbers and numbers that are bigger than whole numbers, right? Like 3 over 2, that's 1.5, that's 2, that's 2.5. These are all greater than 1, so they make things bigger. So these make things bigger. This makes things smaller. So if I'm going to apply this to the n, what I can do is basically just say, well, that's going to make things bigger, and say that, well, that means this has to be bigger than if it didn't have it at all. So 1/2 n over 2 are the two things that I'm going to have to do. I have to have that one, and I have to have that one because it makes things smaller. But if I get rid of the bigger, then I know that this is bigger than this. So get rid of the big stuff, and you make something smaller. Makes sense. So now we know that our a sub n is bigger than 1/2 times n over 2. So if I can show that this is divergent, then I know that that has to be divergent because it's bigger than it. So we go the limit as n approaches infinity of 1 over 2 times n over 2, and that's just n over 4, which we know this goes off to infinity because it's just plain old n. 1/4 of infinity is still infinity, which means divergent. So if you see something's divergent, try to find something that's smaller than it that will diverge as well, and you prove that the other one is divergent as well. So that's what we're having here. That little blue line is the one that's diverging, and it's a lot smaller at the end, right? But if this is divergent, it's going to infinity extremely, extremely slowly, but you can see that it is going off to infinity, right? It's just a line with a slope of 1/4. That's it. That's all that is. It's 1 over 4x. So if that's divergent, so is that. So if you want to show something's convergent, find something that's bigger than it that is convergent, and it locks it in. Like this. If you want to show something's divergent, find something that's smaller than it, and it locks it in as divergent. But putting these together, and you get squeeze theorem. So if you can find something that's smaller and larger, and our general term is approaching it, then they squeeze it together. So squeeze theorem. So whenever you see cosine, and you know by looking at the graph that this is approaching 0, right? We can then just say cosine n pi, all we're doing is really trying to prove it. It's between -1 and 1. So if you now take this, because it's cosine, remember it has between -1 and 1, and we take the next step, we want to always start with something true. And you have options here. We could put an absolute value around it because it is approaching 0. And then that would be from 0 to 1. And then we could just show that that is approaching 0. And then we'd show that the other one as well is approaching 0. But I want to leave it the way it is. And so now we're going to divide it by 2 to the n. See, our a sub n here is cosine n pi over 2 to the n. And I can divide by 2 to the n because we know it's positive. So it's not going to change our inequality. So this is now -1 over 2 to the n is between cosine n pi over 2 to the n, 1 over 2 to the n. And then what I recommend always doing is taking these and plugging them into Desmos because they really do give you that cool little squeeze theorem that's going on. So you can see our general term, as I move it, start to get squeezed in between there, and it becomes 0. So now all I have to do is use my squeeze theorem. So the limit as n approaches infinity of -1 over 2n, and you can change these all to x if you want as well, is equal to the limit as n approaches infinity of 1 over 2 to the n, which is 0. Therefore, the limit as n approaches infinity of cosine n pi 2 to the n is equal to 0. And so there we go, squeeze theorem. Make sure you always have that guaranteed thing that the side on the left's limit and the side on the right's limit, they both approach 0, that they're equal to each other and 0, and then that way it squeezes this in. So our limit of our general term here would be 0. So if you sine, cosine, tangent, plug them in. If you can squeeze it, squeeze it. If you can just use less than, go for it. And if you want to show divergent, you want to use greater than.